Thanks for coming. Today, I want to tell you about some ongoing research program about an out-of-the-box, what I regard as an out-of-the-box generalization of entanglement entropy that is going to be based on two papers that were written together with Fabio Ori and Alex Serantes, as well as, if time permits, upcoming paper written also with my PhD student, Entanglement, and master student, Federica Colombo. So, I mean, you're a diverse audience, and not everyone is working on this topic. Probably not that many people are working on this topic, so please interrupt me whenever you have some questions, comments, and thoughts, okay? Good. So this talk is a very holographic talk. So I'll be talking about ADS-CFT, and the motivation for whatever I have to tell you ultimately comes from top-down sharp geometric probes of the bulk in ADS-CFT. So I mean, like let me make like a few statements. Like the first statement that I want to make is that holography encodes gravity in the language of boundary conformal field theories, and what we know about the bulk, one way or the other, ultimately stems from equality between CFT partition function and the typically semi-classical approximation to the bulk partition function, in which the asymptotic boundary conditions for the bulk fields get identified with the sources for your CFT operators, in particular the metric in which your CFT lives, which is a source for the energy relative tensor operator, becomes the asymptotic behavior of the bulk metric that we fix by hand. Now, when you look at this holographic dictionary, it's kind of obvious that it gives us access to correlation functions, right? Because these correlation functions can be defined by taking functional derivatives of the partition function with respect to the sources, right, and setting the sources to appropriate values. So yeah, I'm like, when we can use the bulk counterparts to perform this exercise and get holographic representation of correlation functions. It also gives us access to thermodynamics. So in order to compute the thermal partition function, what we are instructed to do is to go to the Euclidean setting and make the time direction periodic in your conformal field theory. But this is nothing else than putting a boundary condition on the bulk metric that you consider in your system, right? So indeed, like you can go to this side of the correspondence, construct all the bulk metrics that have this asymptotics, evaluate the gravitational action, pick the one that is minimal, and that's going to give you access to thermodynamics. That's going to be the saddle point approximation to your partition function. And of course, once you have a partition function, then by using thermodynamic identities, you can get an entropy. And then there's like one step farther that you can do, and you can realize this picture or frame this picture in such a way that you get access to entanglement entropy. And this is what I'm going to talk about next. And what I want to emphasize is that all these quantities, correlation functions, thermodynamic quantities, entropies, while all of them are geometric in a sense that in the bulk they are represented by diffeomorphism invariant objects. They are only sometimes sharp in the bulk, in a sense that they do not require the full knowledge of what happens on the gravitational side of ADS-CFT. They actually probe only some smaller part of the geometry. So in particular, one paradigmatic example of such a sharp quantity is a correlation function of two operators that have large scaling dimension. So this delta is large. And in this case, for spatial separations, this correlation function is going to be approximated by a spatial geodesic that connects the insertion points of these operators on the boundary. And so this is the formula. And indeed, such a correlation function does not require the knowledge of the full bulk spacetime, because well, I mean, it only cares about like some particular vicinity of the geodesic ultimately, right? Now, the main background for whatever I want to tell you next is the story of holographic entanglement entropy. It is another sharp observable, and the idea is the following. So let's say that we have like the bulk spacetime. We pick a time slice. So the story is general here. It's illustrated for ADS-3 geometry, but the story is general. So we pick a time slice on the asymptotic boundary. This is where your quantum field theory is defined. This time slice gives rise to a notion of a state in the underlying quantum mechanical description. And in the state living on a time slice, we pick a subregion. The subregion here is this green interval. And then the story is that fundamental entropy of the reduced density matrix, understood in some discretized spin chainy fashion, is going to be given by the area of the external surface that is anchored on this subregion in the bulk. The surface is going to be codimensional too. So in the context of ADS3 is going to be a one-dimensional surface. So again, a geodesy. In ADS4 is going to be two-dimensional surface, etc., etc. And then if there are multiple surfaces that could in principle contribute, then there are two conditions that you have to impose. One condition is that the surface is homologous to the boundary subregion, and that matters, for example, in the black hole spacetime or spherical topology of the horizon. And the other condition is that among these multiple surfaces that all satisfy this constraint, you have to pick the one that has a minimal value of area. So that's the picture of holographic entanglement. Yes.
When you compute things in the bulk, should I think of those computations being done in like a gravitational path integral or some tensor model, or there?
So all these quantities arise in the semi-classical approximation. Mm-hmm. So you might think about at least like as I illustrated them. So like you might think of them as primarily given in terms of semi-classical approximation to whatever is the definition of the bulk. In some particular cases, like what mostly comes to mind is holography defined with respect to double skate SYK. In such cases, you can define a gravitational path integral, and then like some of these notions can be really computed using the proper path integral in the bulk. Good. Any further questions? So let's go. So of course you can ask yourself a question: why these things are interesting? And I would say, for various reasons, but like one particular reason that is relevant for whatever I want to tell you, at least like in whatever way I want to tell you, is that such sharp quantities are interesting because due to their not entirely delocalized nature, they allow to directly probe black hole regions of interest. For example, the horizon, interior singularity. And if such quantities are top down, and we could calculate them independently on the boundary, the match between the boundary calculation and their bulk representation indicates that bulk geometry works, right? That on the gravity side of ADS, indeed, like the geometric picture is correct, not something else, like the geometric picture as given by general relativity. Do you have a question?
Yeah, so something similar. So when you have a heavy operator on the CFC side, you have the dual operator operator, which has largeness.
Yes.
But then you in that cause effect the accessible geometry.
Yes. So I wasn't entirely careful. There's going to be a range of validity for this approximation when you can focus on the GDZ, and that's going to be when the scaling dimension of the operator does not scale with the central charge. If you violate this assumption, then this insertion of operators is going to strongly interact, and then like you have to construct from scratch a new gravitational solution in which there's going to be the Vieira effect as an important effect. And this has been done relatively recently by Pedro Vieira, Ron Myers, and collaborators. And these geometries that they obtain with Vieira, as you suggest, they call spacetime bananas, because there's like some Vieira that emanates from the insertions of the operators and extends into the bulk and looks roughly like the banana. Does it answer your question?
Yeah.
Okay. So this is basically the setting, and now what happened in a beautiful set of works from 2022, 2023 by Tadashi Takayanagi, so one of the proponents of holographic entanglement entropy, and his collaborators, is the following idea. What I want to emphasize is that entanglement entropy is not easy to compute, not only hard to compute in quantum field theory, and there are only a handful of examples when there is a closed form expression for it. And one such an example is 1 plus 1 dimensional conformal field theory in its vacuum state, and the subregion of interest is a single interval. And then you can start with this example and generate all sorts of other examples by applying various conformal transformations. But this is the thing, right? And this result, because it's universal, is gonna have the same functional form in free boson, free fermion quantum field theories, conformal field theories, as well as in holographic quantum field theories. The only difference is that this value of central charge is going to change. I mean, it's going to be 1/2 or 1 in the former cases, and very large of the order of 1/g Newton in holographic quantum field theories. But now you see that the functional form is complete, and then what you might be tempted to do, and this is something that to the best of my knowledge, nobody have really thought about very much before these papers, is to take this result and, regardless of sanity checks, etc., analytically continue it in such a way that the insertion points or like the endpoints of the interval go from space-like separation, where the notion of a subsystem makes sense and the notion of reduced density matrix in a discrete quantum many-body system makes sense, to the case when the interval, the subsystem becomes temporal, like extending along the time direction, like being timeline. But you can do this, right? Because you have a closed form expression for entanglement entropy. You can perform a formal analytic continuation, and the answer that you're going to get now depends on the separation in time, and requires also an imaginary offset. Now, it's not a unique analytic continuation. You can imagine obtaining another expression which differs by a complex conjugation, right? In which instead of plus I pi half, you get a minus I pi half. Good. And you can ask a question like, what is this? I mean, like, does it make any sense to consider such a quantity, or it's something that is completely ad hoc and rather uninteresting? And now, I mean, it turns out that this type of a quantity arose. Yeah, sorry.
On the previous slide, the way you get that formula is you consider just by replica fit, that's multiple copies.
Oh no, even at this level, I'm like I did like what these authors had in mind was something much more down to earth. I would say that like there's a closed form expression. Sorry, there's a closed form expression over here, right? And what you can do is like, because you know it as a function of proper distance, right? Regardless of where these insertion lies, as long as they are space-like, you can simply, like enlarge your function domain also to temporal separations, right? Like that was the idea. It's kind of similar to, I mean, very similar to what happens when you have a two-point function of local operators in your quantum field theory, right? And you analytically continue it to temporal domain, right? Like from space-like to temporal domains, right? And then like things like operator ordering, etc., start mattering, and it turns out that there's like a similar story developing also for this quantity. Yeah. Does it answer the question?
I was just asking that you can also get this formula from consider like multiple replicas of the same system with that.
Yes.
If I do the analytic continuation, am I analytically continuing on each and every slice of this procedure, or formally understand how you're going from left to right?
Yes, I'm like, I would say so, yes. I mean, this would be my interpretation. Because if I'm like, instead of thinking about, multi-sheeted Riemann surface with which are with subregions on each connected in different ways, I can alternatively think about like having like n copies of your CFTs stacked on top of each other and introducing twist operators, right? And then the way I like to understand this is like thinking about this two-point function of twist operators, which are local operators in this case, and another continuing from space-like to time-like, right? Yeah. Now, okay.
This is purely a CFT statement that.
Yes. Yes. I think it was a CFT statement, and now the question is it something that makes physical sense or is completely ad hoc? And this is the subject of the next slide, which is that it does in quantum many-body systems, but not in a way in which entanglement arises. Because in order to define entanglement, like what you just need is like a multipartite quantum system, in particular bipartite quantum system, and then like you just define like density matrix that's relevant for your subsystem. So one factor in Hilbert space, and this gives rise to the von Neumann entropy. Now this generalization that I have in mind is not a generalization that you learn in an undergrad. It's something that is a bit more refined, but at the same time it's not completely ad hoc. Yes.
So when you do analytical configuration, you should have is it guaranteed that there's no branch count, but this produces this stuff.
There's going to be a branch cut because you have to go past the life con.
Right.
And we can talk about it later when it becomes relevant. Okay. Yeah, but that's a good point. Yeah, there's a singularity, and then how you encircle the singularity, how you go around the singularity is going to give you like different answers. Yeah. Good. Yeah. So the quantum many-body interpretation comes from the field of tensor networks. So tensor networks are just quantum many-body ansatz for calculating various quantities of interest in the context of quantum many-body systems that are supposed to be efficiently computable on classical computers, right? Like that's not obvious that it's even possible, because like for some things certainly classical computers with finite resources are not good for, like in terms of quantum mechanics. Like that's sort of like the idea of quantum advantage. But it turns out that there are all sorts of things that you can calculate using classical computers in the context of quantum many-body systems with largely arbitrary accuracy, right? So the setting that we're going to be interested in is a one-dimensional setting, in which case you represent your state in terms of so-called matrix product state, which means basically a product of generalized matrices stacked together in such a way that these legs give connectivity. So such a state can be thought of as for example, a state in the Hilbert space of the Ising spin chain or spin chain of any other sort. And now what we're going to be doing is we're going to be evolving this state in time. And then similarly, what you can do is you can decompose your time evolution operators, like the exponent of the Hamiltonian, into a matrix product operator, right? So like a product of individual matrices. So like each node in this network is a matrix, right? And then adding like a very small, a time evolution of a very small duration in time corresponds to adding like 1 layers of these tensors, right? And then like the more layers you add, like, the farthest you get in time. And if you were to calculate the expectation value of an operator in such a non-equilibrium state, what you would have to do is to add like as many layers as you need in order to go to the time you're interested in, right? Add a local operator and contract with the complex conjugated state, right? So like this whole network now computes for you an expectation value of some local operator, for example, a product of Pauli matrices on 2 neighboring sites, right? So that's just the setting of this tensor network ansatzes. And now the question is what we do with it, right? And the point is that ultimately the expectation value of your operator is going to be given by a contraction of this tensor network, right? So you have to perform a summation associated with product of these matrices over all these links, right? So this is like a vast number. This is a vast number of matrix multiplications that you have to do. And the question is how to do this in such a way that your classical computer is going to be capable of doing this. And one strategy of doing this is to start with your initial state, add like 1 layer of time evolution, and represent like this new object as another structure of the matrix product type, like you have here, right? And keep going until you exhausted all the layers of time evolution. And that's a valid strategy that is used in all sorts of algorithms. But the problem with this is that if you add these layers of unitary time evolution, what you have to do is you have to enlarge the size of the matrices that represent your state. And at some point, these matrices get so big that there's no way of storing them in your computer with a finite memory. And that's the so-called problem of entanglement growth under a non-equilibrium time evolution in quantum many-body physics. But it's a doable thing, and for short durations you can do this. And now there was a brilliant idea that was explored in this paper, starting with a pioneering work by Marie-Carmen Banyuls, Matthew Hastings, and Frank Verstraete, which is not to contract the tensor network like that, but to contract it like that. And yeah, I mean, I don't want to get into technicalities of it, but it turns out that this way of contracting tensor network is in many ways more advantageous. And after the dust settles in this horizontal contraction of the tensor network, the answer for your calculation is given by this object, which is like a contraction of everything to the left and with everything to the right. And when you look at this structure, the structure looks very reminiscent of the scalar product between two states, represented as matrix product states. And now when you have like such a state, left or right state, which is not a state in the standard Hilbert space of your problem, but it's a state in an auxiliary Hilbert space associated with time evolution, discretized time evolution in this case, what you can do is you can define reduced density matrices in time, because what you can do is you can basically take the state, calculate the Hermitian conjugate, and perform partial contraction, leaving some legs open. And this gives rise for you like a notion of a temporal density matrix whose entropy you can compute. So there's going to be three notions of temporal density matrices you can use, like this one and that one. And both are Hermitian objects that give rise to the standard notion of entanglement. Although, like now, like this is related to the extent of your system in time. So the answer for these quantities is just a real non-negative number. But there's also like this generalized notion of the density matrix that arises from this transition amplitude, from the state overlap, in which the density matrix that you get is not a Hermitian matrix. And then when you try to evaluate von Neumann entropy formally of this non-Hermitian density matrix, what you're going to get are eigenvalues that are not real non-negative numbers, but actually are complex numbers. And actually the answer that you get is going to be complex. So I'm saying all this because over here, the quantity that we were getting was a complex quantity. And the leading candidate for what this quantity really is in terms of like many-body system physics, quantum many-body system physics is this type of quantity. So the punchline from this slide, and I understand that most of you or maybe even all of you are not experts in tensor network. The punchline of the slide is that there is a corner of quantum many-body physics amplitude, so literature, in which such a quantity, so entropy of a non-Hermitian generalization of the density matrix, so the so-called pseudo-entropy, makes sense, is very natural to consider, and have been considered before. So it's not an object that is completely alien from the point of view of physics, although it's not an object that you are taught about in your undergrad and even graduate education.
Can you show that in the continuum limit of this tensor matrix that these two quantities go into one are the same?
So let me see if I have a slide about it. No. So there were papers written by Luca Terzacozzo and collaborators in which what they did is they took a particular spin chain that tuned to criticality gives rise to a CFT. They had like a CFT prediction for what such a quantity should be. They did a calculation in spin chain using this type of a quantity, and they got an agreement, numerical agreement, depending like when the spin chain is tuned to criticality, and the subsystem that you're interested in is large, so that you are not sensitive to lattice effects both in space and in time. So this is, I think, like the state of the art as of now.
The numerical.
At this moment, yes, yeah. Okay. So the question that I want to address in the remaining 35 minutes is what is the holographic interpretation of such a quantity that I'm going to call holographic time length entanglement entropy. So let me remind you. For standard entanglement entropy, the idea is that we pick a time slice in your on the boundary of your ADS, asymptotically ADS spacetime. We pick a subregion, and then we look at extremal surfaces anchored at the subregion, and we pick the one that minimizes the proper area. Now, the picture that we're going to have for this new quantity is that we have, again, like this ADS solution. I mean, it can be an empty ADS. It can be black hole in ADS. It can be some excited state in ADS that evolves in time in a non-trivial manner. And then the subregion that we're going to pick is going to be the one that extends in time. So, for example, it can be an interval, or it can be a more complicated subregion in the case of, I mean, for example, multiple intervals in the context of quantum field theory in 1 + 1 dimension, or something more complicated in the context of high-dimensional quantum field theories. And the question is, what kind of geometric diff invariant quantity we have to consider in order to calculate holographic time length entanglement entropy? So there's a question.
Just on the previous slide, is there a reason to, just from the context of these tensor networks, is there a reason to choose the pseudo entropy over any of the other entropies?
Yes, and this reason is not obvious in a sense that when you have these type of contractions, you break these legs. On each of these legs, you can add like some U dagger. On one leg U, on the other leg U dagger. And when you do this, this pseudo entropy is independent of this choice, whereas like these other things might depend on this choice. So in this way, it's like a nicer quantity to consider because it's like gauge independent, so to speak. But the price that you pay is a quantity that is gonna evade like many things that you learned from quantum information about entanglement. Yes.
Sorry, I missed it, but I want to make a trace of T part extending just a 2 to 1 equal time slice, and then you can trace outside, or you also consider.
Oh no. Remember, like the quantity that we're interested in is extending in time, right? So like what I mean is like once, like when you perform the contraction of this complicated network to the form in which you say you pick some site, like for example this site, and you contract everything to the left of this site, and this defines for you this vector. You contract everything to the right of this site, and this defines for you that vector, right? What you do is like you have like this contraction of these two complicated objects, these two vectors in auxiliary Hilbert space that is not the Hilbert space of your ordinal theory, but it's an auxiliary Hilbert space that extends in time. And now what you can do is this is a contraction. So like whenever these squares here are connected by legs, that means that there are some indices over which you have to sum, right? And what you can do, and this is like this partial trace, means that you sum only over some leg connections, and other legs you leave open, right? And leaving them open means that you define a generalized notion of a density matrix, right? Where you have a freedom to contract it, or you have a freedom of just keeping it as a matrix, right? So this partial trace means that we pick the choice to keep it as a matrix, right? And this matrix is going to be associated with cutting these legs open, and this is the object that's going to give rise to pseudo entropy.
Sorry, what do you mean by extended Hilbert? It's a Hilbert space which was supposed to extend it to time.
So that's not a Hilbert space of your original theory. So I call it auxiliary Hilbert space because it has to do with the time evolution of your system in real time, right?
The states are defined effectively such that it is the same product. Or?
Yes, but the point is that like over here the state is in the tensor network language. What you call the state is just a matrix, right? And you don't necessarily have to ask where this matrix is coming from, right? So here what you have is like you have like some left matrix and some right matrix, right? And you can call it a state in some auxiliary Hilbert space, right? Because you can define a quantum many-body system for which like these are going to be some states on their time slice, right? But in the ordinal quantum many-body systems like this one, these are not in the Hilbert space of the ordinal theory, right? Yes.
Yeah. how sensitive is this to the bond dimension that you choose for your tensor network? Because are you always assuming that your bond dimension is large enough that for the time evolution you're considering, you'll never like saturate, like you never saturate the bond dimension? Or
so at the level of the left picture, right? The bond dimension is just going to be the parameter, right, that you choose for that allows you to define like a well-defined notion of time evolution by one step and like the initial state, right? Now the problem arises, like I guess like this is the question of that you want me to address. Like when we time evolve, right? And when we do this contraction in which we define like the time evolved state as another matrix product state, right? Then we have to account for the growth of the bond dimension, right? But now, like what I'm saying, I guess like maybe what you're asking is to what extent.
If you cut it open, so there's an effective bond dimension that you choose there, and like, how big is that?
Yeah, I mean, honestly speaking, I don't remember, but I mean, ultimately, like this kind of a contraction is based on the picture of the transfer matrix that is defined by going from left to right, and then like there's like this intermediate step in which they fold the tensor network. So because they fold the tensor network, what I would naively expect is that the bond dimension that you get over here is going to be the square of the original bond dimension. So this is what I would expect. And then they define the left and right vectors as eigenvectors of this transfer operator. So I would claim naively that would be like the square of the original of the original bond dimension because of this contraction, because of this folding. So it's not huge. And I feel like that was the whole point of this construction, that you don't need to grow the bond dimension very much to be able to perform this type of calculation. Yeah. Okay, so let me get going. And then, let me remind you the question that I want to address, so no more tensor networks. I'm happy to discuss after the talk more, but no more tensor networks. Like the question that we want to address is what's going to be the gravitational representation of holographic timeline and timeline entropy. And there's a proposal, and this proposal was in the original paper on this topic, and the proposal is based on the following observation. So when we calculate the proper length, and we assign a proper length to space-like interval that is non-negative, right? Then if we work in a mostly plus metric signature to a time-like interval, we would be assigning an imaginary proper length, right? And that's not a problem that we get something imaginary, because typically we don't add like temporal separations to real separations, right? So like we just think about spatial with spatial and temporal with temporal, right? And then maybe we calculate the proper distance, right? But then we add squares, so like again, like nothing is imaginary, right? But here, so their perspective was that the analytic continuation in conformal filtering gives you the complex answer, and then perhaps like the real part we can understand as a geodesic segments that give a real value of area, and temporal and the imaginary part as some temporal segment that gives the imaginary contribution to the area. So that was the picture advocated in the original paper. And the problem with this picture is twofold. First, the combined object that you compute in this way is not a geodesic, is not an extremal surface, because space-like geodesics cannot turn and become time-like, and time-like geodesic cannot turn and become space-like. So this full object that was considered in the original paper is made of geodesic segments, but it's not an extremal surface. And secondly, even though like in the context of MTEDS, there is this possibility of such an interpretation, if you go to more complicated setup, it's absolutely not clear what to do. So the first goal that we set for ourselves is to work out a possible prescription for such a quantity and try to apply it beyond ADS3 CFT2. So let me now discuss second goal in real time. Let me just move and discuss the first proposal. And this first proposal is based on a fact that in asymptotically ADS spacetimes, when we have two time-like separated points on the boundary, very often there is no bulk geodesic that connects these points, right? But this statement is not correct. The proper statement is that there is no real bulk geodesic that connects two time-like separated points. But there's going to be other geodesics that connect them, but these geodesics are going to be complex. So our first version of the proposal is that holographic time-like entanglement entropy is going to be given by the Bekenstein-Hawking-like formula, but now applied to complex boundary anchored extremal surface of codimension 2. So that's basically the first iteration that we had in mind. So let me discuss the key features of this construction. So extremal surface means that we don't care if the surface is real or imaginary. We just look that it solves Euler-Lagrange equations associated with a given length functional, subject to proper boundary conditions. Complex means that the surface lives in the bulk metric, where coordinates are complexified, right? So we have like the ADS metric in, say, Poincare patch coordinates. But now what we do is we considered all those coordinates to be, in general, a complex valued objects that have real and imaginary part. And from this point of view, the original ADS geometry is going to be just some particular section of this bigger complex manifold. And now boundary anchored means that the surface, even though like it extends into the complex bulk geometry, it still satisfies the real boundary conditions. That is like, as we approach the asymptotic boundary, we end on the real value of the cutoff for real time separation. So we can do a cross-check, and this cross-check is going to be this single interval case where we know the close answer. So now we're going to be considering extremal surfaces, in this case geodesics. So we can adopt an affine parameterization because we know the length. The length is going to be given by an analytic expression, analytic continuation of a known expression. And if we denote the length by 2 lambda star, then what we can do is we can seek for for length functionals that are going to originate from integration of 1, because we use the affine the proper length parameterization that start at minus lambda star and add on lambda star, such that the total length is lambda star minus lambda star, so 2 lambda star. So there's going to be infinitely many paths that we can consider for this affine parameterization that goes from this value to that value. But then it turns out that there's one particular that is very telling. And this is the one in which we start here, we go parallel to the real axis in the affine parameter plane. Then we go purely along the imaginary axis, and then we go again parallel to the real axis. And when you do this, it turns out that the path that this goes along in the ADS geometry is such that we start on the asymptotic boundary of the real ADS geometry, representing the vacuum of your conformal field theory. We start on the real cutoff for real time separation, and we remain real all the way to Poincare horizon. But so this is this segment. We start on the boundary, we go to the Poincare horizon. We start on the boundary, we go to the Poincare horizon. But now when we are in Poincare horizon, so like at z going to infinity, what happens is that our geodesic wants to go to other section of the solution. And the section of the solution is going to be such in which all the coordinates are multiplied by a factor of an imaginary unit. And when you look at the ADS geometry, multiplying all the coordinates in Poincare patch by a constant factor is an isometry of the solution. And you're instructed in your graduate course of ADS-CFT to consider such multiplications with a non-negative factor. But there is, in principle, nothing that prohibits you from multiplying all the coordinates with a purely imaginary factor. And when you do this, because it's an isometry of your ADS solution, you also get something that looks like empty ADS. And now in this ith ADS geometry, you go along the time-like geodesic. And this time-like geodesic in this ith ADS geometry is the segment over here that connects the path. And what I want to say is that this whole thing that I drew is a geodesic path in the complexified ADS geometry that has the features that each segment looks like a path in the real geometry, but this transition from the blue to red segment is a subtle transition, because what you want to ensure is that the momentum along the geodesic is real, and this multiplying all the coordinates by an I, so entering this other real section of the complex ADS manifold, is what guarantees continuity of the momentum along the geodesic. And this makes this whole path a geodesic path, which looks like patchwisely like a space-like and time-like path, but you have to see it as a path in a proper complex ADS geometry. So this is what our prescription gives in the simplest setup as one possible interpretation. Any questions or comments?
It is still the global, the asymptotic boundary state like a cylinder.
Oh yeah, it's like just a drawing. Yes. But like in the end, like everything happens sort of inside the Poincaré patch. Yeah, and it's complex copy, right? Complexified copy where everything is multiplied by I. Yeah. Yes. Good. So basically we have it, but in a bit of a twisted and subtle manner. But now, of course, the question is if you can, live with it happily and just move on. And the story is that it's more complicated. And it's more complicated because there's going to be situations in which there are multiple external surfaces. And then the question is which one you want to pick. So there are multiple ways in which we can trigger a situation in which there are many complex surfaces. But one such situation will be to consider a black hole spacetime. And now we go from ADS3 to ADS4. This is a black hole spacetime. And the subsystem that we consider is a strip. So it's a situation in which the subregion extends along one space-like direction from -infinity to +infinity. It's entirely localized along the other spatial direction, and it extends in time over some duration, right? And when you look at what's going to be the gravitational solution, so on the gravity side, the solution is going to be an external surface that is anchored on this strip. It starts real, right? Because we want to set the real boundary condition in real slice of complex ADS. And as we're gonna go in, we're gonna see that we start going into the complex ADS spacetime. And then we decided to parameterize this problem as Z as a function of time, where time is gonna be, we choose to be real and choose to be parameter along the surface. And Z is something that complexifies. And then the surface is going to have a turning point. This turning point is basically the tip of the surface in the complex ADS black hole geometry. And a very neat way of understanding the physics of such surfaces is to look at the position of the tip as a function of the separation, so as a function of the size of the subregion. And when you do this, what you're going to get is this picture. So this picture is Z2 symmetric because of the reality of the background that we considered before complexification. And it depicts like two distinct branches of solutions. So like what I want to emphasize is that in this particular setup, there's going to be two distinct types of complex extremal surfaces. And we have to understand what is going to be the criterion that's going to pick one over the other and give rise to a notion of holographic time-like entanglement entropy. So let me discuss these branches. So the first branch is the one that we call vacuum connected, which is the one such that when separation goes to 0, the tip of the surface goes to asymptotic boundary, right? So that's a very natural from the point of view of other things that happen in ADS-CFT, because in ADS-CFT, when we look at probes that are very localized on the boundary, they don't probe deep into the bulk, right? And this is the statement of the so-called UV-IR correspondence. And indeed, like this vacuum connected branch is precisely such that when you are probing short separations, like you're residing in the vicinity of asymptotic boundary, and when you make separations bigger and bigger, you go deeper and deeper into the bulk. And then at some point, actually, what appears is that there is the so-called critical surface, so the surface that does not connect with the asymptotic boundary, along which your solution basically aligns more and more, right? Like that's going to be giving the large time separation limit. So this branch is not exotic, is very usual. It's something that we like. It's something that we have no reasons to rule out. And the other branch, the green one, is such that when actually separation is very small, the tip of the surface goes very deep into the complex bulk. And when we make the separation bigger and bigger, then the tip goes closer and closer to the asymptotic boundary. So this branch is super weird, and it violates UV-IR. And normally, you would like to be able to in some one way or the other to rule it out as the one that you should consider. And then, of course, like this picture is Z2 symmetric. So for these two branches I discussed, there's also like ones that are just complex conjugated. But in terms of physics, they behave in exactly analogous manner. And one thing that I want to emphasize from this picture that I find fascinating is that, of course, we're considering black hole spacetime. So black hole spacetime is going to have a horizon. And when we look at standard fundamental entropy in the context of black hole spacetime, there are theorems that say that the extremal surfaces that arise in this context do not penetrate inside the black hole. But now what you see is that the notion of the horizon of a black hole does not seem to play much role for neither of these surfaces, right? So like these surfaces just do whatever they want to do. They probe the complex bulk in one way or the other, and it's very hard to infer from the way they probe the bulk what is the remnant of the bulk causality in terms of what they do. And I find it quite interesting and something that very worth understanding. And so the punchline is that in this situation, we have two different extremal surfaces, and then there's a question which one to pick. And the natural expectation would be to pick the one that has a minimal real part of the proper area. And the reason for it is that if this quantity sits under an exponent, then the dominant saddle, and typically this is like e to the minus s, the dominant saddle is going to be the one that minimizes the real value of the area. And now what we can do is we can plot the real value of the area, and this is what's done here in this plot. It has a real and imaginary part. And so the real part is the continuous curve. And surprise, surprise, what you see is that for small separations, the real part of this weird vacuum disconnected branch, the one that probes far inside the bulk interior for small separation, is the one that dominates, that has a smaller real value of the area. So if this was supposed to be your prescription, then you would get predictions that are completely at odds with the UV-IR correspondence, that are very different from all sorts of other quantities that you can consider. So on one hand, it looks like something that disqualifies this kind of a branch. On the other hand, perhaps like this is what this kind of a quantity does, and this is what makes this quantity interesting, right? So it's really important to come up with a prescription. that is better than what we have so far. And this led us to the possible second refinement of this prescription, which is to make an additional condition that whatever surfaces that you consider in this time-like case, all of them are analytically continued from the space-like domain from the surfaces that you would consider as contributing to holographic entanglement entropy. So what I'm saying is that you should not look at these. You should not look at these branches just on their own. You should be thinking about these branches, how they're gonna arise from standard holographic entanglement entropy type candidate surfaces when the subregion that you consider is space-like, but then deform this subregion in such a way that it continuously becomes time-like and trace what is happening with all the branches, right? So that's basically the idea that we want to impose. And the working assumption for the remaining 8 minutes is that this green branch is not gonna originate, at least in this regime, from the surface that you would use to calculate holographic entanglement entropy, and therefore has to be ruled out. So the setup that we adopted in the second paper was the setup in which we have this strip subsystem, but the strip subsystem is more general than what we had before, which is we allow this strip subsystem to be either space-like or time-like. And what we're going to be doing is we're going to be varying the single parameter. I mean, this strip subsystem is going to specify by 2 parameters. One is going to be the angle that it makes with the spatial directions, and the other one is going to be the coordinate size. And what we're going to be doing is we're going to be keeping the coordinate size fixed, and we're going to be varying this angle from 0 when we are space-like, all the way to the light cone when we become null, when the notion of entanglement breaks down, past the light cone to the temporal regime where we are interested in, right? So we're going to be doing this in these steps. And ultimately, what we're going to be doing is we're going to be taking a path in the complex angle direction, in which we're going to be complexifying the angle as we approach the light cone to UV regulate the answer, and then go and then reside in the temporal regime. So let me discuss what's happening. So what you have here is a position of the tip of the surface in the space-like regime when things are physics of entanglement, as a function of the boundary separation of the size of the subsystem. And this plot that I'm showing for you, to the best of my understanding, has not been made before, even though this is like a very standard setting of holographic entanglement entropy. This delta that appears here is basically how close we are to the light cone. So we are already very close to the light cone, but we go even closer and closer and closer, while everything is space-like. So the standard notion of entanglement entropy and the standard physics of Rito-kinetic surfaces applies. And what you see here is that when we are close to the light, but not too close to the light cone, for a given separation of the boundary, there is only one solution for the position of the tip, right? So we are close to the light cone, we increase separation, and what the tip does is to move closer and closer to the black hole horizon. So it's something very standard. But now, when we go closer and closer to the light cone, what happens is we're starting getting this bump, and the dependence of the separation on the position of the tip becomes non-monotonic, which means that for a given separation, it's possible to get multiple solutions, multiple extremal surfaces, from which we have to pick the one that has a minimal value of the area. But the beautiful thing that arises from this analysis is that for the coordinate size of the strip that is between 0 and about 10 in the horizon radius, there is always only one solution that exists. So if we define holographic time-lag entanglement entropy in connection with analytic continuation of whatever happens in the space-like regime, for small separations, there is nothing else to analytically continue apart from one particular surface. There are no other surfaces to analytically continue that are real, that are good Ryuta-Kanagi candidates. And then what you can do is you can take these surfaces, you can take this range over here, and you can ask what's gonna be happening as you analytically continue this past the light cone. So here we're gonna go past the light cone by analytically continuing the angle. And what you see is that there is nothing interesting really happening, in the sense that you just go around the light cone and no drama is happening. And now the beautiful thing is that for the separations that are smaller than 10, what happens is as you go in the time lag regime, as you go to the angle being pi half, what you do is you beautifully end up on this, what we called vacuum disconnect branch. And had we chosen to go along the light cone in a different way, so not say above but below, then we would be mapping into the complex conjugated branch of solution, right? So there's a way of obtaining both. But the important thing that I want to stress is that for separations that are smaller than 10, there is only one branch of solutions. So there is nothing else to analytically continue. And as a result, for coming back to the original plot, for this range of separations, only the vacuum connected branch is the one that we have to consider. And then for larger separations, like we perhaps have to consider both, but because we also want to minimize the real part of the area, it's going to be the vacuum connected branch that keeps dominating, right? So the final prescription, and that's basically where I'm going to finish because I'm not going to have time to go through the visitor part. The final prescription for holographic time lag entanglement entropy is to analytically continue all Ryuta-Kanagi candidate surfaces to time lag regime, and if more than one surface exists in the time lag part, minimize over the real part. And in all the examples that we studied, this way of proceeding gives a self-consistent and reasonable definition of holographic time lag entanglement entropy. So that's a good point to break and take any questions if there's. Thank you.
For the normal entanglement, there's like all this interpretation of the entanglement wedge, consistent with like bulk reconstruction and all that stuff. Is there a similar? Do you have a feeling for like a similar interpretation of this time-like entanglement entropy?
I mean, it's a great question that is related to. Let me go to the right plot. Yeah, it's related to this plot. So, as I said. When you look at the density, if you have a black hole spacetime, let's specialize black hole spacetime, right? When you look at what is the part of the bulk that represents like all the things that all the observables that you can compute with the density matrix, right? It's supposed to be the outside of a black hole, right? So like that's basically the entanglement wedge associated with the thermal density matrix. And because what we do here is we ultimately look at temporal observables that originate from time evolution of the density matrix. In principle, you would expect that this should still be the entanglement wedge. But now the thing is that the quantities that we consider do not want to stick to the real section of the spacetime. They want to go to the complex section of the spacetime. And what I expect is happening is that there is a notion of the entanglement wedge that extends also to this complexification of the manifold, right? That coincides with the entanglement wedge of the standard cases when as just a section, but then extends to this whole complex manifold, so that not all parts of this complex manifold are accessible. And I would really like to develop this picture. I think it's there, but this is all that I can tell you. But it's an excellent question. I mean, I've been also thinking about it.
Yeah, that's a really question. And you mentioned some or some generalization to the sitter? How should I think about it? Maybe like.
Yes. So good. So basically, the picture is. I mean, when I presented the paper that discussed this type of quantity, their motivation was twofold. So one part of their motivation was that they were after a quantity that probes the time direction more directly than entanglement entropy, right? So entanglement entropy also probes time direction because what you can do is you can take your entanglement entropy and move from one time slice to the other, right? And in this way you probe the time direction in the bulk of ADS. So that was one motivation of them, that they wanted to have something that probes time direction more directly, not needing to change the time slice, just looking at one instance. And this is what they come up with. But they also had another motivation, which is that if you look at the sitter spacetimes and in poorly defined and poorly understood putative DS-CFT correspondence, we try to ask a question about some probes of the bulk, the spacetime in terms of boundary observables. Then a natural thing that you might be tempted to consider are precisely Rita-Hiranagi analogs, but now anchored on the asymptotic boundary of the sitter, right? And now in the original works and with some correction 2 years after that was triggered by these complex considerations that we did. The picture that you have is that of complex extremal surfaces in asymptotically de Sitter geometries, right? And now the question that you may ask is similar to what we asked: what happens if you have multiple possible surfaces, right? And our idea that we are exploring in this work is to look at some restricted set of setups where we can think about de Sitter physics as being given by analytic continuation from ADS physics, and utilize this type of reasoning to tell you which one to pick. And in some cases that we test, I mean all the cases that we tested, but these are like just a few cases. This is something that works very reasonably. Thanks for asking about this.
Do you think that, or did you?
I mean, maybe that was also like just in, I mean, entanglement entropy sort of scattering. I mean, is there any relation to that?
Oh, with scattering amplitudes. Yeah. Oh, okay. I should have anticipated this question again. Well, yeah, like there are papers, but I haven't been really working on this. But there's been papers about maybe like more like possibilities of scattering in ADS and the physics of entanglement wedge in ADS coming from Perimeter Institute. I think Alex May has been thinking quite a lot about it. So there's been like these types of discussions, but I would say that they are maybe more along the lines of like the physics of entanglement wedge rather than like the physics of scattering in itself. Yeah. I mean, I also know like that people have been thinking about entanglement entropy in the context of scattering, like more like say QCD, etc. But like that's possibly a different stuff. Yeah. Oh, there's one more question.
Just to clarify, when you discretize space-time, then what you compute it as an experiment using the experimental this at the time like interval on the boundary response to that. Some analytic can continue at the your notion of your notion of finite entanglement entropy the entanglement.
But why would I mean, because you're thinking about bulk tensor networks?
Because you introduced this like tensor network thing in the thing, and then you introduced some sort of temporal density state.
Yeah, good.
So do they actually, but yeah, if you discretize them, do they actually?
Good. I would say that in general we don't know. I'm like what I do is I treat this prescription as a standalone definition of such a quantity, and I mean it gives rise to things that are reasonable. And then like if you were to apply this kind of a prescription to your spin chain time type reasoning, I mean, you can also try to do this. I mean, people have been thinking about time evolution in spin chains and like doing like all sorts of cuts through to this time evolution to discuss density images, etc. Right? So I think that can be also looked into. I mean, I think it has not been really looked into apart from some particular number of examples. But maybe like the biggest picture that you might be after is like there's been, okay, but this is in the realm of toy models, right? Like there's been this toy models of ADS CFT correspondence utilizing tensor networks, right?
Right.
And you can ask a question like, what is the physics of these type of quantities in the context of these tensor networks? And I don't know. I mean, I think it's an interesting question to ask, but I don't have an answer for it.
Thanks.
Yes.
Maybe along the side, so is there a complexified version like Mira where you can like complexify the bound, and then you should be able to track like the holographic direction directly.
I mean, that's a curious comment. I mean, I'm not sure. I mean, you seem to know quite a lot about tensor networks. So let me say that Dieter Vidal with Ashley Milstead had a very interesting series of papers around 2018, I believe, in which they've been trying to they've been basically looking at the relation between geometry of path integrals and MERA. So what I mean by a geometry of path integral is something that does not directly connect with gravity. I mean, like this is a statement just about quantum field theory. So imagine that you take your favorite quantum field theory, say 1 + 1 dimensional quantum field theory, and you put it in a given space-time geometry, right? Like for example, like if you want to calculate the vacuum state in a quantum field theory with a gap, what you might be interested in is to put your quantum field theory in half space that is Euclidean, right? Like that's a standard way of preparing the vacuum state, right? And you can ask a question, what is the interpretation of this in the context of tensor networks, right? And then like the answer obviously is that this is gonna be interpreted as like inserting like Hermitian operators associated with, you know, Euclidean time evolution, right? On top of each other, right? At infinity, right? Now, if you're interested in some unitary time evolution, you would add there, you know, like some unitary transformations. But then they started experimenting in these papers, Vidal and Milstead, with coarse graining this tensor network. And they can think about the coarse graining of this tensor network as having to do with the path integral and with some variable cutoff on some particular geometry. And they had like a sequence of situations that they came up with from coarse graining tensor networks, in which they had tensor networks that you might call complex in a similar sense to what I've been talking about, because they had MERAs, like MERA can be associated with a unitary type evolution or with coarse graining, but intertwined also with Euclidean time evolution. So from the point of view of what sits in the path integral is like some kind of like a more complicated object. So yeah, like these types of considerations arise, but it's not. I mean, I would also say that like how time evolution affects MERA is something that has not been really understood. I mean, like at zero approximation, it does not affect, right? Because MERA is a ground state, and ground state is invariant under time evolution, right? But if you were to take MERA at time evolution and cut the path integral to calculate something temporal, right? How to phrase it entirely in the language of MERA, I mean, I don't think people have been looking into this very much. Yeah. Oh, one more question.
Sorry, just to give you my question. Is there any 2 points that in the global ABS the creating a finite time, but if you think Tonka attached it to belong to one?
Yes. You can consider such situations as well. Yes. Yeah.
In your picture, how do you construct the extremes? Yours construct them.
Good. That's an excellent question. So our picture doesn't apply. So like if you look at the original paper that you wrote, in the context of global ADS, we have a restriction on the size of the temporal hypersurface, the temporal subregion that we can consider. That is going to be given by the circumference of of your spatial slice, right? Because only then we can perform this analytic continuation to the timeline case. And that's all that we have to say in our paper. But with Alicia Bernamonte and Federico Galli, we teamed up and started looking into this because one of the reasons was precisely this issue that you pointed out. And you can think of like more general analytic continuations that do not make contact with, you know, like this generalized rotation, right? And when you stick to these, like you can define it for any timeline separation.
So do you do the analytic continuation from the fact that has more than 5?
Yeah, I mean, you start with the picture with you start with the picture of insertions of two twist fields, right? And then what you do is you view them as a function of complex coordinates, right? And then you analytically continue in such a way that the timeline separation becomes arbitrarily big as you wish. Yeah. Yeah. Thanks. I mean, that's a very good point. Thanks for spotting this.
Thank you, Michal.
Thank you.